Okay, I want to thank the organizer of the workshop for having me here. It's pretty exciting to be part of. And I'm going to tell you, my title is very general, and I will not go into tons of detail, although I'll focus a little bit more on a result I was involved in. But I want to give you kind of a big picture of why quantum information theory is a topic that's relevant to quantum Hamiltonian complexity. And because it involves many concepts, please stop me as I go along and ask me to explain things that you'd like to see more clearly. So let me start by giving sort of the big picture of why quantum information theory might be an appropriate thing. And it goes back to really the original motivation for quantum computing in the first place, due to Feynman, who observed that it was hard to simulate quantum systems classically, that if you did it the naive way, you paid an exponential cost. And from this, he realized that, or he raised the possibility that perhaps a quantum computer might do a better job than classical computers. Since quantum systems clearly can simulate themselves without exponential overhead, then perhaps you could even do this in a more controlled way. And from this, the whole idea of quantum computing and quantum computers having computational advantage came from this first observation that a naive simulation of quantum mechanics requires exponential effort. And this exponential effort comes from the phenomenon of entanglement. So if you have n systems, no matter what your theory is, if these systems are in a product state, meaning you can describe the entire collective system by n individual descriptions for the n individual systems, then of course the number of degrees of freedom just adds. You just add up the degree of freedom of each for each one. What entanglement means is that you essentially have an amplitude for all of the exponential in n joint configurations of the system, which means the number of degrees of freedom scales exponentially with the number of subsystems, which essentially is what sort of the technical piece behind Feynman's observation that quantum mechanics scales badly when you try to simulate it. And this describes the cost of simulating dynamics or even of writing down a state. So simply to write down a quantum state on a classical computer generically requires exponential effort. And so in this talk, I want to address the question of when a system is lightly entangled, can we do better? So these are kind of two extremes. A product state has no entanglement at all, and we can simulate it efficiently. We can write it down efficiently, we can simulate dynamics efficiently, everything's great. A completely general entangled system is very expensive to simulate. It's exponentially more expensive. But is there something in between those two extremes? To what extent can we say that something is perhaps lightly entangled and requires less effort to simulate? So I'm going to give you a number of stories of where people have tried to use this kind of reasoning, some successful, some less so, and I'll identify some open questions where we might push in the future. So one story where things have worked, we've understood pretty well, is if you have a quantum circuit. So this is the gate model. You have a bunch of qubits and you apply a bunch of unitary gates to them. So you have n qubits and a series of t 2-qubit gates. And we know that you can do a classical simulation in time that's linear in t and exponential in a kind of entangling parameter k. And k can mean a few different things. So Yaoyun Shi, who's somewhere in the audience, and Igor Markov have proved that you can do it if k is the tree width of the graph, which the graph induced by these interactions, which, if you don't know what it means, it roughly means sort of how far is this graph from a tree? How many vertices do you have to group together in order to make this a tree graph? Another version of this is due to Nadav Uran and Tony Short and Richard Joseph, which is in which k is the maximum number of gates crossing any one of these lines. And so here k is a parameter that interpolates from 0 if there's no interactions between, or 1 if there are no interactions between different qubits, and could scale up to be as large as n, in which case there would be no advantage. And so this achieves the goal I mentioned of having the complexity interpolate between linear if there's no entangling operations going on, and exponential if you have a completely general circuit creating large amounts of entanglement. So in one sense, this is an example of quantifying entanglement and turning that into something which which is able to control the complexity of a quantum operation. On the other hand, it is a little bit pessimistic. It treats all gates as potentially entangling. And it doesn't take into account the fact that perhaps after you do some operations, even though the system could have been very entangled, it in fact isn't very entangled. And so there's a sense, sometimes this pessimism is justified. If you're running Shor's algorithm, you really are going to generate a lot of entanglement. There is no shortcut to simulating that on a classical computer. But there are many, many cases when, in fact, there isn't that much entanglement, and we can do much better. But this is nevertheless one example of the type of interpolation that we would like to see. Another example, which I will not spend too much time on because it's been in a large fraction of the previous talks, are one-dimensional systems. And we think these should be easy classically, or at least we thought they should be easy classically quantumly, because classically they're so easy. Classically, everything you can think of for these systems is easy. Minimizing energy is easy, calculating the partition function is easy, sampling from the thermal distribution is easy. Whatever you like, you can do on a classical, if this is a classical Hamiltonian. Quantumly, of course, it's QMA complete to estimate the ground state energy if you demand 1 over polynomial precision. But in a breakthrough result, or I guess series of results, it was found that if you have a spectral gap which is not too big, not too small, and you don't demand precision that's too small, then you can solve this in a reasonable amount of time. In some cases, polynomial amount of time. If qubits are in a line, and lines are kind of like trees, and Patrick and 2 of his students found, I guess, in unpublished work that this also can be done for trees. And here too we have an example of something where the problem really could be hard. It really is QMA complete, so it could contain a lot of complexity. But by looking at the structure of the problem, we found the parameter that parameterizes the complexity. And in this case, it happens to be the gap. The eigenvalue gap sort of tells you how long range the interactions could be. And then this algorithm was able to identify that as the key parameter that controls the runtime. And so as the gap goes down, the runtime interpolates between something very small and something exponential that matches the fact that this problem is QMA complete when the gap gets small enough. And just to, maybe this is also something you've seen quite a bit before, the intuition behind why these things work, starting with a spectral gap, you can show that correlations decay exponentially at longer length. With additional effort, you can show that implies an entanglement area law, and in turn, an efficient matrix product state description. Of course, all of that is before what they do in their algorithm, which is to find the efficient description. But simply, just to have it is already a precondition. And the history of this is a little bit confusing because Hastings first proved the area law kind of directly by using the spectral gap, and Brandau and Horodecki showed that these 2 steps could be decoupled. So there's kind of a confusing mix of conditions. But in general, if you want one takeaway here, it's that the arrows kind of go from left to right here. That the conditions on the left are sort of the prior ones, and towards the right are generally implied. Except I guess these 2 are equivalent. I should have made that last one bidirectional. Okay, so that's another example of how we found the hard parameter that lets us interpolate between the parameter that controls the hardness. And if I could just take a step back and say, what is the strategy that we want to do here? We want to model a system as a spherical cow, and then add little corrections, like in this case, a tail. And it's sort of the general theme of a lot of physics. You solve a trivial special case, like a non-interacting theory, and then you sort of add corrections to the theory as perturbations, and you're willing to pay a cost that maybe grows rapidly with the number of these corrections. But as long as you understand that that's where your difficulty comes from, maybe it's not too bad. And there's a cartoon that also explains this pretty well. You're trying to predict the behavior of complicated system, then just model it as simple object, and add some secondary terms to account for complications I just thought of. So that's sort of the big strategy, except hopefully the complications we just thought of are really the right ones, and we haven't oversimplified the problem. So that is the big picture here, is to start with a very simple skeleton and then hopefully identify the direction in which perturbations make it harder, and hopefully we identify the right parameter. And since quantum information theory is in the business of quantifying information and quantifying how much surprise there is in the system, how much entanglement, etc., hopefully quantum information theory will have something to say about what are the right parameters to look at. So, and I will mostly focus on entanglement in this talk. I think that I suspect that entanglement is the right parameter. That was sort of the intuition of Feynman originally, and it's the one that people have generally followed since then. But I want to show you just that the situation is not complete. It's not all about entanglement. And there's this strange example that's very simple. It goes back to the beginning of quantum information of stabilizer circuits, which shows how this general picture actually can work in different ways. So what is a stabilizer circuit? Or what is it, rather, a Clifford circuit? So a Clifford gate is a gate U such that if you conjugate a Pauli matrix by it, you get another Pauli matrix. And so by Pauli matrix, what I mean is a tensor product of the single qubit matrices I, X, Y, and Z. So this is a subgroup of unitary gates, and it's generated by a certain collection of single qubit gates, which I won't get into, and controlled knots. And it's very much not computationally universal. It's a small subset of all quantum gates. And it's so, to emphasize it's not universal, Gottesman and Knil proved over 15 years ago that a Clifford circuit can be simulated with a small overhead. The time is linear in the number of gates, and each step can be simulated in time that's basically n log n, if n is the number of qubits. And one way to get some intuition of what mathematically is going on with the Cliffords is that the Paulis can be described by 2n-bit strings, and they sort of look like f2 to the 2n. So a string of 2n elements of f2. And the Cliffords sort of correspond to matrices that act on these, that belong to the symplectic group over f2. That's sort of, so these are kind of like f2 linear operations, which kind of expresses why they can't ever do things that are too complicated and why it might be possible to track them with a simple classical simulation. So if this is the exact theory, this is the simple one, the non-interacting case, how do you interpolate? So this is a very easy extension. If you have k non-Clifford gates and everything else is Clifford, then you can do the same simulation at a cost that's exponential in k. And so you can smoothly interpolate between a Clifford circuit and some general one, but the cost you pay now is not with each entangling gate, but with each Clifford gate. Remember, Cliffords contain controlled knots, which are your sort of classic entangling gate that every experimentalist wants to do. Those are free, but what are not free are single qubit operations that might be non-Clifford. So it's a strange beast, where on the plus side, we can simulate some very entangled computations very cheaply, and that is actually useful because this includes many examples of quantum error correction, which are actually extremely interesting to get practical simulations of, to know how our proposed architectures will scale. On the other hand, so we can do some complicated things well, but some simple things like single qubit gates, most of those it can't do very well. Most of those are non-Clifford, and so you pay exponentially for those. So for a lot of physical systems, it's actually not so good, even though it is good for simulating more complicated things. Yeah?
So is there an interpretation of this simulation, this efficient simulation, as just a special form of some classical simulation? Or is it really just that this is a specific quantum element that doesn't, whose entanglement doesn't wreck you like it usually does?
I don't know. It's pretty similar to simulating non-interacting fermions, but those are still quantum. Does anyone know a way to map this to some simple classical dynamics? One reason why I think it's non-obvious is that one Clifford gate that interacts with, that say interacts only 2 qubits, I believe it still requires n log n time to simulate. And so the locality is completely destroyed by the simulation. And so that's why it's not obvious to me how to translate it to some classical process. But maybe there is something. But no one in the audience is saying there is either. So yeah, so let's leave it as we don't know.
So when you say circuits with k non-Clifford gates are simulable in that much time, is that time on a classical computer?
Yes, sorry, these are all classical simulations.
Yeah.
Right, quantum computers can do this, and these are quantum circuit simulations. You can, these are easy for quantum computers. Okay, good. So, so this is an interpolation parameter that is not, that has nothing to, is really not entanglement. And so, it's. I'm trying to tell you a unified message about entanglement, but honesty prevents me from saying that's the only game in town. However, I'm going to return to entanglement now for more or less entanglement for the rest of my talk. So another example in which entanglement can be tamed, and where we have kind of a succession of where it is basically the relevant parameter, is when we're trying to find the ground state of a local Hamiltonian. So it's a problem you've heard about a lot over the last couple of days, and your Hamiltonian has high degree. So think of your Hamiltonian as it's a 2 local Hamiltonian. Does not mean spatially local. It means that each interaction involves 2 qubits. And so you can think of the Hamiltonian as like a graph. The graph will be D regular. I should say capital D regular is the degree of each vertex in the graph. It's on n systems, each of lowercase d dimension. And this point here about the Hamiltonian being an expectation, this is what's called PCP normalization. And it guarantees that the Hamiltonian has norm that's at most 1. And I don't want to go too much in detail here. I just tried to set the scale of the size of the Hamiltonian. So what you can show in this case, so this is pretty general, a pretty general 2 local Hamiltonian. What you can show is that even though entanglement, ground states of Hamiltonians in general can be entangled, in this case, you can get an approximation that's a product state. There's 0 entanglement. And the approximation quality goes like 1 over the cube root of the degree. So as the degree gets large, you get a better and better there's a product state that there's a better and better product state approximation to the ground state energy. Yeah?
Is this known to be optimal?
The question is it known to be optimal? And you certainly don't have good product state approximations if you have constant degree. I think, okay, so you have our counterexample. Yeah, so that 1/3 on the exponent is probably not optimal. We have a counterexample where that should be replaced either by 1/2 or by 2. And I can't immediately do it in my head which one it is. But our counterexample looks something like that.
So lambda min here is about of the order of n?
Lambda min is on the order of 1. Hence, that was the purpose of the PCP style normalization. The Hamiltonian is an average of local terms. So each h sub ij is a term interacting qubits I and j. And it has norm at most 1. And the overall Hamiltonian is just an average of all of those local terms. So the overall Hamiltonian has norm at most 1. So all of its eigenvalues are within a range of -1 to 1. And so so that means that an approximation error of 1 is trivial, and of 1 over 100 is, the first non-trivial thing you can do.
But you would expect lambda min to be like maybe 1 over n then?
Well,
no.
I mean, think about, suppose these are diagonal Hamiltonians, then this is like,
Then it should be 1.
it's just like a general 2 CSP, right? You expect the unsat value to be anywhere between 0 and 1.
No, I'm just trying to map it to the all the Hamiltonians we've been seeing, the area laws and so on, right? Then it's a sum of the Hamiltonians, right?
Oh, right, yes.
And then the eigenvalue gap you are interested in is constant, so which is like 1 over n.
It's larger than the eigenvalue gap. You cannot.
Yeah, no, obviously.
Thing.
But like n factor larger.
So in your 1D algorithm, the eigenvalue gap that enters, is that for, oh, right. That's where the Hamiltonian is a sum of local terms.
Yeah.
That's right. So the normalization is different from what they do in that 1D algorithm, where the Hamiltonian is a sum of terms.
I see.
Yeah.
So what's the symbol, the fancy E symbol?
Expectation, it means an average over ij. So that I tilde j means edges in the graph, means pairs I and j that are connected. So the Hamiltonian is a, you have a bunch of qubits, and they interact according to some there's interactions that correspond to some graph, and there's an interaction here. On each edge, you have an interaction, and the overall Hamiltonian is the average of all of those interactions.
Yeah, so I think the trick is that you are like Umesh and Zef and others, like they just sum it up, and you are taking the expectation.
So I'm dividing by the total
so
number of
you are
interactions.
dividing by, actually you are not dividing by n, you are dividing
By
n
ND.
n times d.
That's
and
right.
That's important that there is this d.
Oh, that's
and
right.
That makes the trick, right?
That's right.
Because the d is in the denominator in your formula, and
That's right.
first
So-
I was surprised. How could it be in the denominator?
Right, because otherwise you could add dummy edges. You could add edges where the Hamiltonian on that edge is 0, and the approximation would get better. And you should be suspicious about seeing such a thing. Yeah. Another question? Yeah.
Intuitively, is this another result of monogamy? That as
Yes.
you increase the number of interactions?
Yes. Yes.
It's
I'll come back to that in a
question?
second.
What was the question?
The question is this an example of monogamy of entanglement? I'll come back to that in a minute. I would say, monogamy of entanglement is sort of, I would call it an intuition rather than a theorem, because there are many manifestations of it. But I'll actually come back to it quite a bit in coming slides. Good. So one consequence of this is because there's a product state approximation for the energy, that means the ground state energy can be approximated within NP. You can write down a product state efficiently because it has a small classical description. Of course, there are other things that have small classical descriptions. This is just one of them, but it's one of the more convenient ones. And so you'll hear tomorrow about the quantum PCP theorem, and this says if you're going to prove a quantum PCP theorem, you had better not take the degree to be too large. So you can think of this as you like, as sort of backing the quantum PCP theorem into a corner. We already know that it has to be on an expander. Now you know also that it has to be an expander, but also the degree cannot be too big. So, which is, of course, quite different from the classical case, where classical PCPs are perfectly happy to have very large degree. And the intuition, I've told this result to physicists who have told me that it's been long known. And then when you push on it, then they say, well, actually, I guess the proofs from long ago proved it in some very special case. But it is sort of an intuition from physics that there's something called the mean field approximation that applies as the degree of your interaction gets higher. So what people often do is start off with a line and then consider 2D and 3D, and then you might as well take the limit to infinite dimensions, which you can either have a complete graph, or you could have it be this thing called the beta lattice, which is like a Cayley graph.
It's not a tree. I thought beta lattice is a tree.
Yeah, I know. It's not a. It's sort of a not really a lattice.
No, but is it a tree?
Yes, it's an infinite Cayley tree.
Oh, I see. It's that Cayley graph. Okay.
It's the Cayley graph of the free group.
Okay.
Yeah. And people have often, so what people do in physics often is they just pass the limit of infinite dimensions and interpret it as either a complete graph or this infinite tree. And you can prove that in these cases, then entanglement is usually not you can often prove in these cases that entanglement is not an important part of the solution, that you can neglect entanglement for the purpose of the solution. And then you can reason if it's true here, then probably it's true for high degree in general. And in fact, it's a good enough approximation that it's often already true in 3 dimensions. So already 3 dimensions, there are many cases when it's already described well by this mean field intuition. So it's been a pretty productive way of thinking about a lot of systems. And it can also be thought of in terms of the monogamy of entanglement, that if a particle is entangled with one, the particle cannot be entangled with all of the other ones simultaneously. And so if there's going to be entanglement, then it cannot be, it cannot be relevant to most of the edges. It can only be relevant to a small fraction of the edges, which can be neglected to get the sort of error that I'm talking about. So the approximation that we prove actually is a little bit more complicated, a little more sophisticated than the one I mentioned before. What I said before is a special case. The general theorem we prove allows for the possibility of grouping the vertices, the qubits, into clusters, and then getting an approximation which is not product across the individual systems, but product across the cluster. So you allow entanglement within each group, but require it to be product across the clusters. And now, this is the error term that you get, which is quite a bit more complicated, but let me unpack it. First, let me define this phi of x sub I is the expansion. So x sub I is a subset of vertices, and phi of x sub I is the expansion of that subset. And what that means is if you choose a random edge in the graph that has one endpoint in that set, what is the probability that that other endpoint will be outside of that set? And the average expansion, you can also think of it as the fraction of edges that go between clusters. So that's the first term. And question? No. The next term is the familiar 1 over degree that we had before. And this last term is the average over I, so the average over clusters, of the entropy of the cluster. So I want to explain a little bit this notation. So when Ashwin talked about entropy, he wrote it as a function of the density matrix, of S of rho. And here I'm writing as a function of the subsystem. And the way to relate those notations is I might, if you have a density matrix, rho, on systems A, B, C, ... then you can define rho sub A to be the partial trace over all of the other systems. So rho superscript A means I'm just considering system A of the overall density matrix. And when I write S of A sub rho, I mean S of rho superscript A. So this means entropy of those systems, and I'm just reminding you that the state is rho with the subscript. And this notation is better in cases when we have a single state that we're always considering, but we're looking at many different subsystems of it.
So Aram,
yeah.
So what it says, this statement says.
Yeah.
So I am wondering about that because it says something counterintuitive. Because, like you are saying, so you want to approximate the ground state. And
Yeah.
And the way how you are approximating it, your state has no entanglement inside the clusters.
Yeah.
And has entanglement outside.
No, the other way around. It has no entanglement across clusters.
So no entanglement across clusters.
No entanglement across clusters.
Oh, between clusters. Oh, that means across. Sorry. Then,
Yeah.
Then it's sort of the message is clear.
Okay, good.
Yeah.
Yeah, Zeph?
So just something that Mario said. You're not actually getting. So to what extent are you getting a picture of what the ground state is? You're not, right? It's just some approximation of the ground energy, but
That's right.
But that range of energies includes what proportion of the space?
Good. So the question is, this produces an approximation, but to what extent is it an approximation of the ground state? And it's not, actually. It approximates the ground state energy, but the fidelity with the ground state could be very, very low. It could be... think of this, I guess this might be clearer tomorrow when you hear about PCP, but when you hear about PCP, people will talk about violating a constant fraction of the constraints. And so you make errors in a small constant fraction of positions. So you can think of this as agreeing with the ground state in 99% of locations. I mean, very, very roughly. That's the level of approximation that we want, which of course means that the fidelity will be very small. Good. So to
Could you define what's phi again?
phi is the expansion of that set. So let me go over what these terms are. So this means this is a good approximation if any one of three conditions is met. So the first is if you can cluster it into non-expanding sets, you get a good approximation. And that's really nothing new. That was known. That's known for classical constraint satisfaction problems. It's really not very surprising because if you just delete all the edges between the clusters, you haven't deleted very many edges. So that's sort of not very surprising. But we get to combine it with all the other things at once. So that part is nice. Second, we have a good approximation if degree is high. That I think is surprising. That's new to quantum states. And finally, we get a good approximation if entanglement satisfies a sub-volume law. So this was asked about earlier. Does an area law imply a good approximation? And here we have a result that says we have a term that's the entropy of a subsystem divided by m, the size of that subsystem. And so if this is, the most this can be is 1. If every subsystem is maximally entangled with the rest, that term is going to be 1, and it at least will not hurt the rest of the argument. Right? It just goes away. And if it's much less than 1, then it will mean that we have a good approximation, even if all the other terms are as bad as possible. And so this being much less than 1 is called having a sub-volume law. You have a volume law if the entropy of a region is basically equal to the size of that region. And you have a sub-volume law if the entropy is much less than that. And so in this case, it says that if you have a sub-volume law, so really less than the maximum possible entanglement, or substantially less than the maximum possible entanglement, then you can go further and even get a product state approximation. So it's really quite a jump to go from less than the maximum amount of entanglement to saying, in fact, we can get up to an approximation with no entanglement. That will be a pretty good one in terms of the energy.
So,
Yeah.
so actually, I would like to go back to the simple case when
Yeah.
we just have the graph.
No clusters, yeah.
So no clusters because that's
simpler to understand.
That's the important message, right?
Yeah.
And so there, the message is: I am trying to formulate the message, and tell me if I am wrong.
Yeah.
That if so, as Sanjeev asked about these parameters, so if the ground energy is really close to 0, then this approximation says nothing. But that's when that's when actually the quantum effects kick in. Like if the ground energy somewhere is close to 1 or some kind of constant, so that's when your approximation says something, and so then actually the system looks pretty much like classical because, well, you can approximate and you can approximate with a product state. So this is how I am interpreting it.
I think I'm misunderstanding. So
completely wrong.
You're saying with the ground, so the ground, all the eigenvalues of the system are between -1 and 1. So you're saying if they're kind of at one extreme or the other?
Yeah, so if...
Well, lambda min, I mean,
Yeah.
this approximation is useful when lambda min is of the order of, bigger than this error term. Right?
Yeah, I mean, there's nothing... yeah, I mean, it's useful when... you see, lambda min is not naturally positive or negative. We have no...
I get you. So it's kind of
we have the a priori bound we have on it is maybe that it's at most... I mean, you might... The approximation is useful when no simpler method would do better than it. So one simpler method is just add up all the norms of all the Hamiltonians in the system, average... take some trivial bound of the norm, like just average all the norms of the things that go into it. Is it, and ask, is it better than that? But it's, I think it's non-trivial as soon as the degree is bigger than some universal constant, like 100 or something. Yeah.
So it's related to what Mario is saying.
is it a good way to understand it in the frustration-free case when when all the terms are positive semi-definite and you want to understand whether the ground energy is 0 or something which is say a constant? Like, as far as I understand, if one of these conditions hold, for example, it means that the qPCP cannot hold, right? This is the way it should be interpreted.
Yeah, degree is right. That's right. That's right. But what does it mean for qPCP to not hold? It just means you can get a pretty crappy approximation, right? PCP is, these are approximations that screw up a small constant fraction of the constraints. So, frustration-free, that's still asking, is there a single constraint that's violated or 0 constraints? And it's very, very far from that. This is the weakest kind of approximation that's non-trivial. Yes. Which I would call the PCP range. I'm hoping, I don't want to dodge questions, but there will be a lot of PCP tomorrow also. I just want to mention that.
I think I still don't understand the role of capital D, or maybe I should define the expansion by capital D to get a unit-free object. You can explain better why that comes in the denominator, I'm not sure.
Well, that's the whole, so intuitively, it's because of monogamy of entanglement. Each vertex interacts with D other vertices, and it can only, let's suppose, here's a toy model of monogamy of entanglement. Each system can be entangled with only one other system. And so if you do a product state approximation, then for one of those bonds, you've done a terrible job. And for D minus one of the bonds, you've done fine. And so only a 1 over D fraction of the bonds have been screwed up. That's why a toy model of monogamy of entanglement would imply that you'd get some kind of 1 over D error. And on the next slide, I'll give you an actual argument, but that's a sort of a hand-wavy version of why. So let me, maybe I'll do a sketch of the proof, which follows this technique of Prasad, who's somewhere in the audience, and his collaborator Ning Tan, which is this information theoretic technique that when Fernando and I discovered it, we wrote 2 40-page papers immediately, following up on all the implications, and then I think we're still not done following all the uses of it. It was very exciting to see this formula, and it's surprising because it's not a very hard formula, but somehow it came as a big shock to us. And the formula is the chain rule for mutual information. And I don't know if anyone defined mutual information before, so let me just do it. So,
classical or quantum?
Either one. So in both cases, the mutual information is the sum of the entropies of 2 systems minus the joint entropy. And the conditional mutual information is if you make all of these conditional on a third system. So whenever you see entropy, replace it with a conditional entropy. And you can think of this as how much does Alice know, how informative is Alice's state about Bob's state? And this one can be how informative is Alice's state about Bob's state given already having knowledge of Charlie's state. And that way lets you interpret the chain rule of mutual information, which says, so the sort of the baby version of the chain rule is that the mutual information between A and BC is equal to the mutual information between AB and the mutual information of AC conditioned on B. So this is how much does Alice know about the BC system together? Well, as much as she knows about the B system, plus the amount she knows about the C system conditioned on her knowledge of the B system. So that's the chain rule of mutual information. And there's no, it's just expanding out these entropy quantities and canceling terms. There's nothing to the proof. And if you repeat it, you can say, what is the mutual information between a system X and a series of systems Y1 through YK? It's the mutual information between X and Y1 plus between x and y2 conditioned on y1, and so on up to x and yk conditioned on all the ones that come before it. So that's just an identity. That's just doing these kind of things, expanding out these kind of terms and canceling things. And what you get from it is something actually kind of profound, which is if this x system has dimension d, then the left-hand side is at most log d. But the right-hand side has k terms. So the smallest one of those should be pretty small. It should be at most log d over k. We don't know which term, so let's call it t, the particular term. But it means that at least one of those systems, x should be uncorrelated from at least one of the y sub t's conditioned on all the previous ones. And so what this means, if you have a collection of n systems, is that if I choose indices I and j1 through jk at random, then for some choice of t, I will have conditional near independence. So xi and xj will be nearly independent once I condition on j1 through jt. And here I've just renamed jt plus 1 to be j. So I choose a bunch of things at random and condition on t of them, and then condition on those, an average pair of other two systems will be nearly independent. So this is just basic classic information theory, but it already gets us most of the way home. Because what it says is that if we discard these systems that we condition on, well, that's at most k systems. So if k is small, maybe that's not too much error. And the resulting probability distribution is nearly independent for all pairs. And the only thing we have to do to relate it to our actual problem is we have to say, well, this was an average over all pairs. We have a particular graph. Okay, I've erased it, but we have this particular graph describing interactions. What we really care about is how independent are you across the edges of that graph. And so there we have to pay some, that level of correlation across edges of the graph might be much higher than the average correlation. And it might be higher by a factor of n over d, because that's how many more edges there are in the complete graph than in our particular graph, which is d regular. So that's sort of the essence of the argument. If you condition out a bunch of systems, then you're nearly independent across all of the edges in your graph. Now you might be a little worried that everything I said was classical. There's nothing quantum here, so how much of this argument still goes through quantumly? So some parts still work. So the chain rule still works. Pinsker's inequality, which you need if you want to go from mutual information being small to trace distance being small, that still works quantumly as well. One thing that's not so good is that you can't condition on quantum information. So in this last one, we had to condition on the states of the things of the J1 through JT systems. That no longer works quantumly. You can't condition on the state of a quantum system.
So what are A, B, C in this quantum setting? Events?
A, B, and C are systems, are subsystems. So you have a quantum state on several systems, like qubits. Think of them as you started off with n qubits, and A, B, and C might be individual ones of those.
Okay, values of those qubits. Those are random variables.
They're the quantum analog of random variables.
Quantum variables. Right?
Yeah, that's right. Another new difficulty is that we want to argue that if you're conditioned on a third system, you have almost no mutual information, then you must be nearly product conditioned on those. And yet it does not. It turns out to not imply that your state is nearly separable. And here too, I believe that no one has defined separable states before. Is that? I'll define it anyway in case you don't remember the definition. So the set of separable states is the convex hull of all product density matrices. So these are the states that have no entanglement, that have only classical correlation. And if conditioned on a third system, 2 A and B are completely independent, then that means that they are separable. It means that that third system is like a classical index, and the system of AB is written as just a convex combination of completely independent things. However, this does not hold approximately. If your system is if the conditional mutual information is approximately 0, that doesn't mean that you are approximately separable. So there are things here which are mathematically somewhat difficult. However, there's a very easy resolution to a lot of them, which is we can just map to the classical problem. So we can just measure every system, or imagine that we measure every system, using something called an informationally complete measurement. And all that means is that from the measurement statistics, you have enough information to reconstruct the original quantum state. And it's well known how to do this. You get some distortion, so the information is all there, but the distinguishability of the quantum states goes down by a factor that's polynomial in the dimension. And in particular, what this looks like is if m is your quantum measurement, then the trace distance of the measurement outcomes is at most the trace distance of what you started with for your quantum states, and at least a 1 over a polynomial in d factor times the original trace distance. And this formula, the middle term here is a distance of probability distributions, a classical variational distance. And these terms here that sandwich it are a quantum trace distance. So it lets you relate a classical and a quantum trace distance. So just with this measurement, that's enough to essentially complete the proof. Once you put together the proof, what does it look like? You measure an epsilon fraction of the qubits and condition on the outcomes. Then this says that most other pairs of qubits would have low mutual information if you were to measure them. And this means that their state is within this distance to product. That's the loss that you get from your informationally complete measurement being imperfect. And so the resulting witness is a product state across all of the systems, and the total error has these two contributions, and all you do is you choose epsilon to balance those two terms.
D cubed on the previous slide.
What term are you proving here?
That should have been d squared on that slide.
Okay, so my follow-up question is that an artificial loss of your argument? Because in your baby version of monogamy of entanglement, I think we would have gotten a log d in the numerator.
Oh, that's right. So we've lost this extra polynomial factor
so
of d.
this may be an artifact.
That's a good point. We should talk about it afterwards. I cannot prove to you that poly d factor is necessary. We haven't tried too hard to optimize it because usually think of d as small. But it's an interesting question whether that poly d
your
factor.
implications for PCP seem to really, that plays a role. So because you have the trade-off between capital D and little d in your.
I think little d is not such a big deal. Little d is, I put that in there to be complete, but I think it's fine if little d is just some constant, like 2, always. But still, it's interesting to know. Yeah?
Why would it have relevance to the quantum PCP? Because in quantum PCP, the d is constant. No? Even when you are making the after the transformation, the small d is still constant. So I don't see.
No, your target is constant d, but if you were to prove quantum PCP with d, which is log n, for example, there would be a larger result.
But even then, d squared would not be a killer, or maybe.
No, it means it allows you to take capital D also log n, right? If you let small d be log n, and not have this rule out in the result.
But so now, what is your conclusion? That there is no quantum? What is this piece?
No. In terms of quantum, it's a partial no-go. If that doesn't disprove it, it says that if quantum PCP were to hold, then the degree of the interaction graph should not be too large. It should be essentially constant. I think that's the conclusion of this. And any small clustering of the system should satisfy a volume law for entanglement. In addition to the thing we already knew, which is that it should be an expander.
Yeah, that's interesting.
Okay, so I don't want to talk. I'm sick of talking about quantum PCP, so I'm going to skip my little motivating slide of why quantum PCP, even though it's arguably more fun than the dry equations. But let me tell you more technical stuff. Because I began by talking about a hierarchy of approximations, right? About you pay more, and then you get a better approximation. And that's missing from what I told you, right? So what happens here, you can pay more by having a bigger clustering, but there's no way to pay more and just simply get a guaranteed improvement of your approximation. So what does the approximation quality depend on? Well, the degree, and that's just given to you. That comes from the graph. You're never going to change that. It comes from the average expansion of your clusters. Maybe a bigger clustering will drop that average expansion, but maybe not. You don't have control over that. It depends on the graph. And it could well be that as you cluster more and more, the things are always expanding a lot. Also, the average entropy. Again, it may well be that as you cluster more and more, your systems always have a volume law. And so there's no way to sort of spend more to take a larger witness and get a systematically better approximation. And so that is, I think, an unsatisfying piece of this work. However, I will now tell you about a way in which, and we have found a way to spend more and get more in doing so, but with partial success. And what that is, so in the same paper that developed this, we also looked at a case in which you could find that ground state approximation efficiently. So everything I said before is about an NP approximation. Just does a good product state exist, but it gives you no help in finding it, and it may well be NP hard to find it depending on your problem. So one way you can attempt to find it is by using an SDP hierarchy. And this is something I'll talk more about tomorrow. But I just want to briefly mention today that a possible algorithm for doing it, which is to optimize over the following semi-definite program, take your variables to be all density matrices for subsets of k or fewer qubits, or qubits, whatever, systems. And then what constraints do you impose? Well, one obvious one is if two of these subsets overlap, they should be consistent on the overlap. And there's another one which is a sort of global PSD constraint, which I'm going to define tomorrow. So let me just not say what it is now. But if you're familiar with Lasserre, then you'll know that there's another global constraint that shows up. So in a different paper by Prasad and his co-authors, I think it was with Bose Barak and David Stirrer, they showed that this works for classical constraint satisfaction problems when k, so k now is a parameter. As you turn it up, you pay exponentially more, but your approximation gets better. And Prasad and his co-authors showed that this works when k is much larger than the threshold rank of the graph. The threshold rank is the number of large eigenvalues of the adjacency matrix. And we can show that this works in the quantum case as well, at least when you have a good product state approximation. So you can find a good, this works classically, is what they showed, and we showed that it can find also a good product state in the quantum case. And also, of course, as k converges to n, this will eventually give you the exact answer. If k is equal to n, this is just exact diagonalization. So at that point, you're spending exponential time. So this does interpolate between something very cheap and something that's expensive and gives you the exact answer. However, there's something still unsatisfying about it, which is the only type of state it will ever return for you is a product state. It will not give you some family of increasingly entangled states that converges to the right answer, but it gives you the only way we could figure out how to return a state from this is to get a product state. And just to put in context how this works, we have the true ground state energy, and we have two types of approximations to it. So there's one type which is called a variational bound, and this is just come up with a model of a state and plug that in and calculate the energy of that. And that was the first theorem I told you, where you come up with a product state. That's an example of a guess for the ground state. The ground state is the one with the lowest energy, by definition, so any other state you plug in will give you, whatever that energy is, will give you an upper bound in the ground state energy. So the variational bounds give you upper bounds in the ground state energy. Now this SDP is a relaxation. You optimize over density matrices that are locally compatible but may not extend to a true state for the entire system. And so this is a relaxation in that one possibility is that this includes the possibility of using the ground state's true reduced density matrices, but it also includes some spurious density matrices that do not extend to a global solution. And so it will always give you something that's less than or equal to the true energy. And so in practice, people like to use both of these methods, because if you find that they're close, then you have a rigorous proof that the ground state energy must be in a narrow range. But there's something missing from a theoretical point of view, which I think is a great open problem, which is this SDP relaxation improves with K. As we turn up K, we provably get a better and better approximation that approaches the right thing. But the variational upper bounds are stuck. The only one we have are product states. There's no systematic way of getting better and better ones. In 1D, we have matrix product states. But if there's no natural 1D structure to your system, we don't have a way of systematically getting better approximations. So I think that's a kind of a great problem to figure out in the future. And I think that doing so may require better being able to quantify entanglement. And I have essentially 0 time left for my talk. Is that about right? Let me, in any case, take 1 minute to say that, here we have pure bipartite entanglement, what Ashwin talked about. Mixed entanglement is a total mess, and I've listed here a ton of entanglement measures for mixed quantum states. And the only thing we can really agree on is that separable states should have 0 entanglement, and pure states should have entanglement corresponding to their entropy. I want to show you, this is a table of the properties of different entanglement measures. This is a set of relations between different mixed state entanglement measures from Matthias Kristandel's thesis. It is a complete mess. And I think that one of the challenges is, can we come up with better entanglement measures that really do quantify in terms of, like we had in such a nice way for quantum circuits before, is there some kind of nice entanglement measure that could quantify the hardness of approximating quantum systems? Another approach to this is via conditional mutual information, but I'm out of time and we'll skip that. And we'll also skip this topic, which is a very nice one. And I'll also skip the question of dynamics. And I will conclude by saying, with an open question, which is, if we do believe that exponential quantum speed up, or conversely hardness, is because of entanglement, then how can we make this quantitative? And the answer may include some subset of better entanglement measures. So a lot of the previous ones, I think, have not been very operational or have not been very easy to compute, not connected to computational topics. So we would like to do a better job with entanglement measures. We would like to have better classical ways to describe quantum states. We had my work with Fernando had some partial success with product states, but we really need to find a way to systematically improve those. Matrix product states are one way that are really great. They work well in 1D, but not otherwise. The answer may include better understanding conditional mutual information. You saw a little bit of how it came up in my proof of the PCP no-go theorem, but there's a lot more we can do. And also this thing I didn't quite mention, which is approximate quantum Markov states. So even if I skip some of the details, I think you can appreciate that having a systematic way of describing the complexity of quantum states is a desirable goal, and hopefully quantum information theory can help us do that. Okay, thanks for your attention.
So we can take 1 or 2 questions.
If you had had a chance to speak about dynamics, what would you have said?
right? So for dynamics, what are dynamics? It's time evolution of a quantum system. So that means Hamiltonian and then some noise terms. And we know in terms of noise per gate, if you have very little noise, then you have fault-tolerant quantum computing. That's just BQP complete. You have universal quantum computing. If you have a lot of noise, classical simulation is possible. But there's this big intermediate regime that we don't really know what to say about. And is there some, here's the question that I think we'd like to answer. Could we simulate lightly entangled dynamics? Namely, if you knew the entanglement was always less than k, then can you do some simulation that runs in overhead exponential in k? And not only is the question open, but I don't even know how to define the question, because what does it even mean for entanglement to be less than k? I think defining that is like a big part of what's missing from it.
How about the separable case? I mean, go to 0.
So exactly. So we know only we know the extreme, and we don't know how to perturb it.
For dynamics?
Yeah, we know that if the entanglement is always 0, you can simulate it.
That's pure states or
Pure
for
states.
mixed states?
Mixed. So actually, this is an old paper of me and Michael Nielsen. That was like my third paper, like back in the day. And it's pretty easy. What happens is, suppose you have some noisy dynamics so that you never create any entanglement. Then you start off with a pure state by assumption, and then you take one step, and you get a separable state. And this separable state is a mixture of product states. So you just sample one of those, and it's not a very complicated separable state. It just involves 2 qubits, so it's not so hard to sample. And that's it. Now you have another product state, and you keep going. And you've simulated the evolution. So if you have operations that do not create an entanglement, then you're fine. This is different from the whole NMR thing. That's another beast. But this is for non-entangling operations. So
the operations are...
yeah, that's what we know, is that the operations are non-entangling. And that's sort of... So I put up the D-wave picture because, a lot of people like me, are very skeptical of D-wave achieving anything useful. But if we want to prove that D-wave has not achieved anything useful, the only way to prove that is, I think, with a classical simulation of something that's a good approximation of their model. And we know their model has a lot of noise, but you have to really say that the parameters of their noise are ones that can be classically simulated. I think only then can you really conclusively say they haven't done something useful.
What was the rounding procedure for your SDP hierarchy? Was it just taking the marginals?
You have all marginals on k systems. So choose a random k-1 set of systems, measure them in some informationally complete way, and then look at the kth one. And then as you move that kth one around, you get an opinion of each one of the individual systems. So you're just rounding to a product state, that's enough. And now you can perhaps see the difficulty of rounding to anything more complicated than a product state.
Okay, one last question.
So you said about your result on simulating non-entangling dynamics of supervelocity. So do you expect that a perturbation of that should be true? Because
I mean, the problem is if you're allowed to generate a little bit of entanglement in one step, you can just repeat that step a bunch of times. So it's hard to perturb it. I don't know how to perturb it. I think what you need is some kind of promise that you never develop too much entanglement in some sense.
But I don't know if it's totally relevant or not, but it reminds me of this DQC model where we know that this entanglement is always low across any car.
Well, it depends on what measure you use, I guess. Right? So I think we haven't found an entanglement measure that would lend itself to efficient simulation. I mean, maybe there is. Maybe this research agenda can be shown to not work. But that's what we don't know yet.
Right. So let's keep some energy for the last talk and thank Aram.